Derivatives of exponential and logarithmic functions. We start off with an exponential graph. We have graph of y equals e to the x, and something magical happens here. Are you ready? Are you ready to watch this? So if I draw a tangent line on e to the x and mark it at 0, 1 right now, the slope of that line happens to be 1. So it has that point in common. And as I drag my tangents and graph the new slopes, what do you notice? The two graphs are exactly the same. This only happens once in all of calculus, and it happens with the equation of e to the x. If you have e to the x and you want to find the derivative is e to the x. And so it doesn't change, which is going to cause all sorts of problems. Well, not problems, but sometimes when things change, you feel like you've done something right. You've actually accomplished something. When things don't change, you're like, I'm done. So if your question is, you have e to the x, what's the derivative? E to the x. I haven't really done anything, but that is the right answer. Of course, now we can apply all of our other rules as we go through. What happens when you have a number in front of a function? Does that affect the derivative? No. So if you started off with y equals 5 e to the x, the derivative would be 5 e to the x. Can someone tell me what the 20th derivative would be? If you did that 20 times? Good. Nice. It wouldn't change. If you had to work backwards, if you got a derivative of 4 e to the x, that means originally it would have been 4 e to the x, but this one would have been an x to the 5. There would have to have been a 3 out in front. Oh. Plus 8. Or whatever number you want. You don't need a plus 8 there, but you could. Find the equation of the tangent to y equals e to the x at the point 0, 1. Draw the graph and the tangent line so we get a picture. So we have to remember what the graph of e to the x looks like. The graph of e to the x has a horizontal asymptote at y equals 0. It's going through the point 0, 1. The next point you could figure out would be, if you plug in 1 for x, you would get e for y. And so here's the graph, and we want to find the equation of this tangent line. Whoa, wanted green. There's green. At the point 0, 1. To find an equation of a line, we're going to need a point and the slope. We already have the point. We know that it's going through 0, 1. We just need to find the slope. How do you find the slope of a tangent line? Well, your derivative tells you all the slopes. So if we did the derivative of e to the x, we would get e to the x. And at x equals 0, we would get dy dx equals e to the 0. And anything to the exponent of 0 is 1. So we know that our slope is 1. Now to find the equation of the line, in this particular case, I would use y equals mx plus b because I know my y-intercept. My y-intercept is 1. I know my slope is 1. So the equation of that line, the green line, is y equals x plus 1. No problem. Now, what would happen if we changed a number a little bit? Okay, so I had y equals e to the x. That one happens to be exactly the same. If I changed it to, what's close to e? 3. 3 is close to e. Oh. Just wait, cancel. Is it still on there? Yes. I want to get it at 0, there we go. Does it work? Is it perfectly the same? Oh, close. So the next question we have right now is, if I had y equals 3 to the x, how do I write my derivative? Oh, that's good. 3 to the x-ish. Sure, that'll be well seen everywhere. They'll like that a lot, right? In fact, you might start using it on all of your answers. You just add ish to the end of everything. But it's really close. So here's something new for everybody. If we do have a different base, then your derivative is going to be b to the x times by the natural log of b. Can you see that this still works if b is equal to e? If I have e to the x, could I make my derivative e to the x times the natural log of e? Yes, because the natural log of e is 1. So now the question is, why does this work? Or why do we have that extra natural log in there? Where does that come from? Okay, so if you had y equals 3 to the x, what I'd like you to do is I would like you to do some algebra and see if you can rewrite 3 to the x as e to the something. Can you do that? So a little review from last semester. If I wanted to solve for that question mark, and I had the equation 3x equals e to the question mark, anytime you're solving for an exponent, you could do that by taking the log or the natural log of both sides. So I'm going to take the natural log of both sides. Why am I taking the natural log? Because I have a base of e. So if 3 to the x equals e to the question mark, then natural log of 3 to the x would equal natural log of e to the question mark, since they're equal. What does my log laws allow me to do? It lets me take my x out in front. It would also let me take my question mark out in front. What's the natural log of e? The natural log of e is equal to 1, so I just get my question mark has to equal x times the natural log of 3. What does that mean? That means that 3 to the x is equal to e to the x times by the natural log of 3. Now, if I have y equals 3 to the x, and I want to find the derivative, that derivative would be the same as if I had started with e to the x times the natural log of 3. And what do we know about the derivative of e to the x? It stays the same. But do you see that we have a function inside of e to the x? So we would have a chain rule. The chain rule would say e to the x stays the same, multiply by the derivative of the inside function. Natural log of 3 is a number. What's the derivative of a number times x? Just that number. So that means my derivative is equal, well, this part right here is the same as 3 to the x. And then I have an extra natural log of 3 after. According to our formula for anything b to the x, which could be 2 to the x, 5 to the x, 10 to the x, you will always have that natural log of that number afterwards. And this is a little explanation of why. Because we could rewrite any power as e to the something else. So what does that mean if we wanted to find the derivative of something? Any exponential will stay the same and then multiply by the natural log. And here we just have a nice regular power rule. Next graph to look at, the natural log. If the derivative of e to the x stayed the same, will the derivative of natural log stay the same? No. There we go. What graph does that look like? Have you seen that shape before? Does it look like it has an asymptote at 0 and an asymptote at x equals 0? And did you cheat and look ahead in your notes and see that it was the 1 over x graph? Well, technically it's only part of the 1 over x graph. Because the 1 over x graph, if we remembered the 1 over x graph completely, the complete 1 over x graph has this part which we saw, but it also has this part. In this function, though, it just has the part on the right because the domain of natural log of x is only when x is bigger than 0. That's why on our graph we only got part of the 1 over x graph. You can't take the derivative of any x values less. Now this one, unlike e to the x which looks the same, this one is confusing because it looks so different than what you started with. So if we had y equals 5 natural log of x, the 5 itself stays there. The derivative of natural log is 1 over x. So we could say that our final answer for this one would just be 5 over x. Now, similar to exponents, the 1 over x only works when the base is e. What happens when we change the base to something else? So the question, if we do it with a number, who wants to use their favorite number? We're not going to use negatives. 343, okay. Log base 343 of x, and we want to find the derivative. So the question is, could you change log base 343 of x to using a different base? And here, do you remember the change of base theorem? If not, we'll review it right now. The change of base theorem for logarithms says if you have a log base a of anything m, you can change it to any base you want and I wrote that b in blue to really point out that that blue is only on one side of the equation. It lets you choose whatever you want for that. And it really doesn't matter because it's not connected to the left-hand side of the equation at all. So that means I can change log base 343 of x to the natural log of x divided by the natural log of 343. And the natural log of 343 is just a number. So I could rewrite this as 1 over the natural log of 343 times by the natural log of x. And my derivative for this one would be the same as what we just did with the 5, although 5 is probably a number you're a little bit more familiar with than 1 over the natural log of 343. Right? Probably sometime in your life someone said, guess what number I have in my head, and you said 5. Probably never in your life did someone say, guess what number I have in my head, and you said, is it 1 over the natural log of 343? Although try that next time someone says, guess what number I have in my head. I guarantee you will be wrong. So now if we wanted to do the derivative of this, well, the 1 over the natural log of 343 would stay, because it's just a number, and the derivative of natural log of x is 1 over x. So we could write this as my answer is 1 over x times the natural log of 343. Can you see how that matches up with the new formula? It still has the 1 over x, but you have that natural log of b in your denominator. And this is the reason why. Now, you don't have to use the change of base theorem every time to do that. If you want to memorize this as another logarithm, that's fine. However, if you know where something comes from, your chances of remembering it are better. So here the change of base theorem really helps. What's another way you could do this? Let's say you forget. Let's say you forget the change of base theorem. Another way you could do this is take this equation and change it from log form to exponential form. Do you remember that 343 is the base? That the y on this side would be the exponents because logs solve for exponents, and it would equal to x. If I wanted to solve for y in this equation, I could take the natural log of both sides. Oh, this is a good review of logs. And then your y could come out in front. Divide both sides by the natural log of 343, and we get the same thing that we got before with the change of base theorem. The change of base theorem did it directly. This was using my definition of a logarithm, changing it to exponential form, solving for y by taking the log of both sides. And I took the natural log of both sides. What the change of base theorem says is you could have taken the log of any base of both sides and it would still work, which would get you what your change of base theorem says. You can pick anything for b. The reason we chose the natural log of x is because we already knew the derivative of the natural log of x was 1 over x. Or at least I told you. We have to say, I guess technically, I just told you this. We haven't proven this, right? In some levels of higher math, you'd be asked to prove this. You could try your definition of your derivative. It's not going to work out nicely. So something to look at is saying, how would you prove this? And if you wanted, you could look it up on Google, but that is the job of a mathematician. They notice a pattern. They say the derivative looks like 1 over x. How would I prove it? And once you prove that, we've showed that you could prove these other ones easily. Yes?
Why is, like, when you times 1 by the natural log of x, like, why is that just 1?
Which line are we looking at? From here to here, or from here to here? Well, from here to here, I'm doing the derivative. Okay? So this number is just a number, so it stays in front. And then the derivative of natural log of x is 1 over x. And then from here to here, it's just multiplying fractions and putting things together. Okay, so now you've learned the new rules for exponential functions and new rules for logarithmic functions. And now we're ready to put all the rules together with those as well. Okay? Constant in front, does that 2 do anything? If it's just a number, that number would just stay out in front. What's the derivative of log base 7 of x? Well, any log's 1 over x and a base 7.
Sorry for the interruption. Mr. Hayes, please contact the office with your location.
Why isn't this a product rule? Why shouldn't I make this a product right there? Because it's just a constant in front, right? There's no function in front, so we don't have to worry about a product rule. But if that was a function in front, then we would have to use a product rule. Oh, nice segue. Okay, so let's rewrite this into forms that we know. Every time we have a square root, we have a half. Can you see in this one that we do have a product right there, and we do have functions on both sides of that product with x? So now we're going to use our product rule, which says keep one the same, so I'll keep the first one the same, times by the derivative of the other one. So we keep one the same and we change the second one. Perfect. Then we keep the second one the same and change the first one. Half comes out in front, subtract 1 from the exponent. Done. And of course, this one would look something completely different in your answer key because they would change this to a square root on the bottom. They would factor out the e to the x. They would get a common denominator. So make sure you keep practicing that every time you do a question. Again, can you see the product rule? Okay, I'm going to get you to try this one and the next one on your own. How did you do? Okay, you could have either left it like the second line, or if you wanted to factor out a 3x, you could. All right, check on this one. Quotient rule. Keep the bottom the same, derivative of the top, minus keep the top the same, derivative of the bottom, over the bottom squared. Another quotient rule. I will also show the answer for this one. If you had started off by writing it like this, you could have done the product rule as well. So again, you could choose the quotient rule or the product rule. Either way, both of them would need to be simplified in a textbook. This one, when you multiply it out, you'll get an x to the 6 on the bottom. This one, you'd have to factor out an x to the 4 in your numerator, and then you would get an x to the 6 in your denominator as well. So as a start, rewrite your equation. And then we have a chain rule because the square root of x, or the x to the 1/2, is inside of e to the x. The outside function is e to the x. So you do that derivative first, which means everything stays the same. That's what the e to the x derivative does. And then we multiply by the derivative of the inside function, which is that x to the 1/2. And of course, you could simplify this from here. Now, one of the things that I find so fascinating in this one is that if I did a little bit of simplifying, I'm not going to oversimplify, I'm just really wanting to simplify what's inside those brackets right there. If I simplify it inside those brackets, what's going to happen with the 5 and the 5? Cancel out. And I get this. Okay? Now, you can simplify the 3x squared and the x on the bottom, but this is a really interesting discussion piece because I'm just going to open up a new page here. Zoom. Okay. When I have the natural log of x, the derivative is 1 over x. And I just had the natural log of 5 over x, and the derivative is 1 over x. So if I had the natural log of, just to over-represent a number from earlier today, 343x, what's the derivative? 1 over x. Why? Why does that number not matter? Does that bother you? A little bit? Why does that happen? Well, we could explain it with the chain rule, because the derivative, I mean, if we did it the long way, the derivative is always 1 over, so that would be on the bottom. But then the chain rule says derivative of the inside, you'd have to multiply by another 343. And so those numbers always cancel out. So we could explain it with the chain rule. Can you explain it to me another way? Why that happens? Why is it that the natural log of 343 times x is also equal to 1 over x, but you are not allowed to use the chain rule to explain it? So I can't use this, but I still want to show why the derivative is 1 over x. No chain rules allowed. And you can't say, well, I used the chain rule with the numbers 1 up to 342, and they all worked, so 343 has to work as well. That's not allowed. What also could we do? What could you do with this? Can I rewrite this in a different way? Yes. Obviously, if I ask it that way, the answer is yes. But how? Do we have a rule? Do we have a rule when we multiply inside of a logarithm? Oh, yeah. What's the rule? The rule says you can add. And if you add, natural log of 343 is a number. Don't know what that number is, but it is a number. What's the derivative of a number? 0. Plus, what's the derivative of natural log of x? 1 over x. So there's another way to explain why, when I had the natural log of 5x, the 5's canceled out and it was the same. But again, it's a good thing to help us think about our log laws and see and remember them. Oh wait, that was exciting. Back to this one. Is there a log law for adding inside of a log? No. Although people like to make them up, right? Number one way to get logarithm questions wrong is to make up laws. Then you'll get the questions wrong. This is a chain rule. We see a function 1 plus 6 of x inside of natural log. So we do the derivative of the outside function first. Derivative of natural log is 1 over whatever, and then we keep the inside the same. So this part here, 1 over, keep the inside the same, then multiply by the derivative of the inside, which is just 6. Product rule, keep the 7x the same, then derivative of e to the x to the 4, where derivative of e to the x to the 4, keep the inside the same, and this one was probably okay because the inside was in the same places where it should be, and then multiply by the derivative of the inside. Then keep the second one the same and derivative of the first one. And 1 to go. Whenever I have this situation where it looks like it could be a quotient rule, but the number on top is a constant, I like to change it to a negative exponent. So the cube root will be a third, but I'll move it up to my numerator to make it a negative a third. Then all I have to do is my chain rule. So where does my chain rule? What's my most outside function? It's the power of negative 1/3. So I bring that negative 1/3 in front, keep the inside the same, subtract 1 from the exponent. Then I have to do the derivative of the inside. Well, derivative of 7 is just going to be 0. Derivative of e to the negative 3x will be e to the negative 3x, but it's another chain rule where I have to do the derivative of the inside, so I have to multiply by negative 3 as well.